Hey students, Professor Nugent here. With this video, we're going to continue discussing interaction effects as another way to represent nonlinearity in regression functions. The interaction effects that we're discussing in this video are interactions between two continuous variables. With the regression you see here by this big rainbow star, we have two continuous independent variables, x1 and x2, and as specified, the effect of x1 does not depend on x2, the effect of x2 does not depend on x1. To allow the effect of x1 to depend on x2, we need to include an interaction term. That is, we're going to generate a third variable, which is the product of x1 and x2, as you can see here in this third term. Alright, so this allows us to represent the way that the effect of x1 depends on x2. So let's compare the various cases. We'll look at the effect of x1 on a change, the effect of a change in x1 on a change in y. So we see the original value in b, and then a change in the value of x1 and a change in the value of y in a. Subtracting a minus b, we get the following expression. The change in y is equal to beta 1 times the change in x plus beta 3 times x2 times the change in x1. We can rewrite this expression so that the change in y over the change in x1 is equal to beta 1 plus beta 3 times x2. So the effect of x1 depends on x2, which is what we wanted. And beta 3 represents the increment to the effect of x1 from a unit change in x2. Typically in practice, when we want to discuss the effect of x1 on y, we will substitute in the mean of x2 here. Let's look at an example where we have our prediction of test score equal to 686.3 minus 1.12 times the student to teacher ratio minus 0.67 times percent of English learners plus 0.0012 times an interaction effect of the student to teacher ratio and the percent of English learners. The estimated effect of a class size reduction is nonlinear in this case because the size of the effect depends on percent of English learners. So the change in test score for a change in the student to teacher ratio is equal to negative 1.12, and that comes from the coefficient on the student to teacher ratio plus 0.0012 times the value of the percent of English learners. So when the percent of English learners is small, then this increment is going to be small. When the percent of English learners is high, this increment is going to be high. And we can see that here, when percent of English learners is 0, the predicted change in test score for a change in the student-to-teacher ratio is negative 1.12. When percent of English learners is 20%, then the predicted change in test score is negative 1.1. So this is a very effective way to model nonlinearities, and as we have discussed in class, This is especially useful because it does not remove or strip information from data in the way that using dummy variables or generating dummy variables from continuous variables does. Let's finish this out with some statistical inference. We can ask whether the population coefficient on the interaction effect is equal to 0. That is the null hypothesis, that the interaction effect is equal to 0, with a t statistic of 0.06. We cannot reject the null that the coefficient on the interaction effect is equal to 0. Likewise, we can ask, does the population coefficient on the student-to-teacher ratio equal to 0? With a t statistic of -1.9, that's just less than -1.96, and so again, we cannot reject the null at a 5% level. Now, it's important to carry out a complete set of statistical inference and ask whether the coefficients on both STR and STR times PCTEL are equal to 0. And in this case, we get an S statistic, which is 3.89, with a p-value of 0.021. So we reject the null that both the coefficients on the student-to-teacher ratio and the student-to-teacher ratio times percent of English learners are equal to 0. So what's going on here is that there is imperfect multicollinearity in this regression between this variable and this variable, which causes this standard error to be large, because it's hard to identify this coefficient holding that variable constant. Right, folks? And so we're likely to get the result that these individual coefficients are equal to 0, but when we test the joint significance, where we are going to find, in this case, that either one or the other or both are in fact statistically significant, important for test score. They enter the equation. That's it for continuous interactions, and I will enter my opinion here. Whenever you have variables that are measured on a continuous spectrum, then it is often most useful to use that variation to its fullest extent and then complete that with the interaction, rather than stripping information from the data set by categorizing into dummy variables and running your interaction effects that way. So this is probably one of the most useful examples of interaction effects.